Hello and welcome to Earth Science, Lecture 13, Crustal Deformation. Mountains provide some of the most spectacular scenery on our planet. Poets, painters, and songwriters have captured their splendor. Geologists understand that at some time, all continental regions were mountainous masses and that continents grow over time through the addition of mountains to their flanks. Where lithospheric plates collide, the rocks in the collision zone are crumpled and transformed. Even continental interiors hold the remains of mountain ranges formed after ancient collisions. Young mountain belts tower above the surrounding landscapes, exhibiting steep-sided slopes and high relief. When the tectonic forces that raised these mountains cease, weathering and erosion will, over long periods of time in a geological scale, grind them down until their roots lie flush with the surrounding topography. Even then, their rocks hold clues to their former grandeur and the forces that created them. So this is a two-part lecture. We're going to start with the forces that create them, here with crustal deformation, and then look at the process of building actual mountains in Lecture 14. Tectonic forces can cause rocks to move, tilt, and/or change shape. For instance, colliding plates can uplift flat-lying beds of marine limestone so that they are exposed to the surface. They could rotate them so that they lie at a steep angle, or they could crumple the rock layer into folds, sort of like you see in the image. Collectively, all of these types of change are called deformation. Rock deformation is caused mainly by tectonic forces, and it occurs mostly along plate boundaries. That is, the place where lithospheric plates push together, pull apart, or scrape past one another. Rocks deform in a characteristic way that can be observed when the rocks are exposed on Earth's surface as an outcrop. For example, the folds represent a typical response to a compressional force at depth. Geologists use the term tectonic structures or geological structures for the structure features that can be observed that reflect a rock's tectonic history. This lecture will examine three types of tectonic structures: folds, faults, and joints. Rocks respond to stress, which is what takes into account the area over which a force acts. So in other words, stress is force over area. Deformation is caused by differential stress, in which the force is stronger in one direction than another. We will consider three types of differential stress: compression stress, tensional stresses, and shear stresses. On a large scale, each type of stress tends to be associated with one type of boundary. So, the first type is compression. This is when differential stress that squeezes a rock mass as if it were in a vise, and this is what we call compressional stress. Compressional stresses are most often associated with convergent plate boundaries. When plates collide, Earth's crust is generally shortened horizontally and thickened vertically. Over millions of years, this deformation produces mountain belts. Differential stress that pulls apart rock bodies is known as tensional stress. Along divergent plate boundaries, where plates are moving apart, tensional stresses stretch and lengthen rock bodies horizontally, but thin them vertically. For example, in the Basin and Range province in western North America, tensional forces have fractured and stretched the crust as much as twice its original width. Differential stress can cause rocks to shear as well, which involves the movement of one part of rock past another. An everyday example of shear is the slippage that occurs between individual playing cards when the top of the deck is moved relative to the bottom. Shear is important at transform plate boundaries, such as the San Andreas Fault, where large segments of Earth's crust slip horizontally past one another. Rocks experience three types of deformation that leads to shape changes: elastic, brittle, and ductile. Elastic deformation. If you open a door that has a spring attached to it, when you let go of the door, the spring pulls the door shut and it returns to its original shape. We say that the spring undergoes elastic deformation. That is, it deforms temporarily in response to a stress, in this case the force that you use to open the door, and it returns to its original configuration when the stress is removed. Chemical bonds in a mineral grain act like a spring. When they are elastically deformed, they stretch instead of breaking. When the stress is removed, they snap back to their original shape. The energy released by most strong earthquakes comes from the stored energy that is suddenly released when a rock elastically snaps or rebounds back to its original shape. When a rock's strength is exceeded, that is, when it is deformed beyond its ability to respond elastically, it will either break or be permanently bent. Rocks that break into smaller pieces exhibit what we call brittle deformation. From our everyday experience, we know that glass objects, wooden pencils, ceramic plates, and even our bones exhibit brittle deformation when their strength is surpassed. Brittle deformation occurs when stress breaks the chemical bonds that hold a material together. When an object changes shape without breaking, we say that it has undergone ductile deformation. When you knead clay or taffy, you are deforming it in a ductile way. Ductile deformation in rocks takes place largely through the mechanisms described earlier: slippage along surfaces of weakness within the rock and the gradual reshaping of the mineral grains. These processes enable rocks to flow very slowly, even though it remains in a solid state. Intricate folds are an example of ductile deformation. So there's a lot of information to take in the beginning. We have another bulleted list here. Rock deformation tends to be brittle at shallow depths and ductile at greater depths. 4 factors influence how a rock will deform. That is, temperature, confining pressure, the type of rock, and time. So let's go ahead and look at the 4 factors that determine the deformation. First is temperature. Temperature plays a major role in the behavior of rocks. Where temperatures are high, that is, deep in the Earth's crust or next to a heat source such as a magma chamber, rocks are near their melting temperatures and are therefore weaker and more capable of ductile deformation. Near the surface or in a completely cool environment, such as subduction zones, rocks are more brittle and prone to fracture. This behavior is completely familiar. A cold chocolate bar snaps between your teeth, whereas a warm one will bend in your hand. Recall that the confining pressure on rocks increases with depth as the thickness of the overlying rock increases. Because confining pressure squeezes rock equally from all directions, it tends to make them harder to break, and hence less brittle. Thus, at depth, the increase in temperature and the increase in pressure have complementary effects. The increase in temperature enhances ductile behavior, and the increase in pressure tends to keep the rock in contact, it keeps it intact, and it is thus more likely to bend rather than fracture. The manner in which a particular rock type responds to stress is also greatly influenced by its mineral composition and texture. Granite, basalt, and well-cemented quartz sandstones are examples of strong, brittle rocks that tend to fail by breaking, in other words, by brittle deformation, when subjected to stresses that exceed their strength. By contrast, however, clay-rich or weakly cemented sedimentary rocks and foliated metamorphic rocks more readily exhibit ductile deformation. Weak rocks that are most likely to behave in a ductile manner, that is, bend or flow, when subjected to differential stresses include rock salt, shale, limestone, and schist, for example. The central non-foliated layer behaved in a brittle manner, breaking into chunks, while the flanking foliated layers responded to the same differential stresses in a ductile manner, flowing into the gaps between chunks. You can create the same effect by biting into a s'mores. The graham crackers break, while the warmed marshmallow and chocolate layers ooze. Rock salt consists of intergrown crystals, so you might think that it would resist ductile deformation. In fact, the opposite is true. Salt crystals readily change shape by recrystallizing in response to different stresses. This is why salt layers can rise up through other strata to form salt domes. Glacial ice also consists of crystals that deform easily, accommodating internal flows. And last but not least is the factor of time. So, the folded rocks of mountain belts show that tens of kilometers of compressional strain or shortening can be accommodated by ductile deformation. For this to happen, stress has to be applied slowly enough that the sluggish process of ductile deformation can keep up. If stress is applied to a rock unit too quickly, the rock will deform elastically until its strength is exceeded, and then it will fracture. Taffy exhibits the same behavior on a more familiar timescale. If you hit a bar of taffy against the edge of a table, it may break. But if you put a weight on it and leave it overnight, it will gradually spread out and flatten. In practice, rocks that are near Earth's surface tend to accommodate even gradual strain by fracturing. Ductile is what happens at depth. Along convergent plate boundaries, rock strata are often bent into a series of wave-like undulations called folds. Each layer is bent around an imaginary axis called a hinge. Folds in flat-lying strata are much like those that would form if you were to hold the ends of a sheet of paper on a flat surface and then push them together. Such folds come in a wide variety of sizes and configurations. Some are broad flexures in which strata hundreds of meters thick have been slightly warped. Others are very tight, even microscopic structures found in metamorphic rocks. Most folds result from compressional stresses that result in a lateral shortening and vertical thickening of the crust. Folds are also described by their axial plane, which is a surface that connects the hinge lines of the folded strata. In simple folds, the axial plane is vertical and divides the two folds into roughly symmetrical limbs. However, the axial plane often leans to one side so that the limb is steeper on one side than the other. So there's a lot of definitions here, but just note that we're talking about folds, so rocks that get bent. Each side is a limb, and in the middle we have a hinge where it gets bent by. And this plane dividing the two sides is called an axial plane. So we're going to look at the two main types of folds, anticlines and synclines. The two most common types of folds are the anticlines and synclines. Anticlines are usually formed by the upfolding or arching of sedimentary layers. Typically, found in association with anticlines are downfolds or troughs called synclines. The limb of a syncline may also be adjacent to the limb of an anticline. So up top you see an anticline where it's folded upward, and you see the downwarping feature here of a syncline. For me to remember which is which, I think the letter A points up and down like this, just like the fold that it creates. Depending on their orientation, these basic folds are described as symmetrical when the limbs are mirror images of one another, and asymmetrical when they are not. The limbs of a symmetrical fold dip at the same angle, resulting in a vertical axial plane, like you see in the first two images. By contrast, the limbs of an asymmetrical fold dip at different angles, which results in an inclined axial plane. An asymmetrical fold is said to be overturned if both limbs happen to dip down in the same direction, like you see in the bottom right image. That is, one limb is tilted beyond the vertical of the other. An overturned fold, like the one you see in the bottom right, can also lie on its side, so that the axial plane is horizontal. These recumbent folds are common in highly deformed mountain belts such as the Alps. So here I've just included an image showing you a topographical map showing how these work. So anticlines and synclines typically work together. I mean, if you just move this middle photo down a little bit, it almost lines up with the other one. So you can see upwarping anticlines and downwarping synclines right next to one another often in the real world. And sometimes, because of certain stresses, you can get an overturned fold where both sides are dipping, in this case of the top right image to the bottom left. When a broad upwarping of basement rock deforms the overlying cover of the sedimentary strata to produce a circular or slightly elongated bulge, the feature is called a dome. The Black Hills of western South Dakota represent a large structural dome generated by upwarping. This is the image on the right. Here, erosion has stripped away the highest portions of the overlying sedimentary beds, exposing the older igneous and metamorphic rocks at the center. Structural domes can also be found or formed by the intrusion of magma, such as laccolith. In addition, the upwarping migration of buried salt deposits can also produce salt domes like those beneath the Gulf of Mexico. Salt domes are economically important rock structures because when salt migrates upward, the surrounding oil-bearing sedimentary strata deforms to form oil reserves. The inverse of a dome is a downwarped structure termed a basin. Several large structural basins exist in the United States. The basins of Michigan and Illinois have gently sloping beds similar to saucers. These basins are thought to have resulted from large accumulations of sediment whose weight caused the crust to subside. A few structural basins may have resulted from giant meteor impacts as well. Because the sedimentary beds in structural basins usually slope at low angles, basins are identified mainly by the age sequence in their strata. In a basin, like you see on the image B in the middle, the youngest rocks are at the center and the oldest are on the flanks. However, on a dome, like you see in part A, such as the Black Hills, the reverse is true. The oldest rocks form the core and the youngest are on the outside. So something is pushing up these older layers up to the surface again. So at the center you see the older layers and then it gets younger as you go out, and vice versa for our basins. Just going to throw in one other interesting feature that we might occasionally find on the surface. Although we have discussed folds and faults separately, they may occur together as a result of the same tectonic stresses. One example can be found in a broad regional feature called monocline. Particularly prominent features of the Colorado Plateau, monoclines are large step-like folds in otherwise horizontal sedimentary strata. These folds appear to have resulted from the reactivation of ancient steep-dipping faults located in the rock below the plateau. As large blocks of basement rock were displaced upward, the comparatively ductile sedimentary strata above it responded by draping over the fault like clothes hanging over a bench. Displacement along these reactivated faults can exceed 0.6 miles. So let's discuss faults a little bit more. So we're going to spend the next several slides looking at the different types of faults that we find. Before we begin though, let's cover the basics. Faults and joints are both structures that form where brittle deformation leads to the fracturing of Earth's crust. A joint is a fracture, whereas a fault is a fracture along which motion has occurred, so that the rocks on either side are offset from one another. So this is a really fascinating image. It shows a small fault revealed in a road cut, where the sedimentary beds have been offset by a few meters. Faults of this scale usually occur as single discrete breaks. By contrast, large faults like the San Andreas Fault in California have displacements over hundreds of kilometers and consist of many interconnecting fault surfaces. These structures, described as fault zones, can be several kilometers wide and are often easier to identify from aerial photography than at ground level. Sudden movements along faults is what causes most earthquakes on Earth. However, the vast majority of faults are remnants of past deformation and are now inactive. So the first type of fault we are going to discuss, and this one we'll discuss in a number of slides, is called a dip-slip fault. Faults in which movement is primarily parallel to the slope of the fault surface are called dip-slip faults. In this case, dip refers to the angle at which the fault surface is inclined. So dip-slip faults are whenever you have a fault, so from here, from top left to bottom right, with motion along it, so parallel to that fracturing. These names were first used by prospectors and miners who excavated metallic ore deposits such as gold that had precipitated from hydrothermal solutions along inactive fault zones. The miners would walk on the rocks below. The miners would walk on the rocks below the mineralized fault zone and hang their lanterns on the rocks above. Rapid vertical displacements along dip-slip faults tend to produce long, low cliffs called fault scarps, which you can see on the top. The movements that form such scarps typically are generating earthquakes as well. So you can see two terms here. We have the hanging wall block and the foot wall block. So the foot wall block is the one that's sitting below, and the upper surface is the hanging wall block. So just keep this in mind. We have a hanging wall block, which is the one on top, and the foot wall block, the one on bottom. When the hanging wall block, or the one on top, moves down relative to the foot wall block, dip-slip faults are classified as normal faults. Normal faults are associated with tensional stresses that pull rock units apart, thereby lengthening the crust laterally but thinning it vertically. This pulling apart can be accomplished by either by uplift that causes the surface to stretch and break, or by horizontal forces that have opposing orientations. These faults are called normal faults because it is normal for gravity to pull a block of rock down an inclined plane. Normal faults occur in a variety of sizes. Some are small, having displacements of only a meter or so. Others, however, extend for tens of kilometers. Most large normal faults have relatively steep dips at the surface but tend to flatten out with depth. Dip-slip faults in which the hanging wall block moves up relative to the foot wall block are called reverse faults. So it's the same type of fault where motion is along the fault line, but in this case it's the opposite direction. A thrust fault is a type of reverse fault in which the fault's angle is less than 45 degrees. Reverse and thrust faults result from the compressional stresses that produce horizontal shortening of the crust. In other words, two pieces of land moving together. Most high-angle reverse faults are small and accommodate local displacements in the region dominated by other types of faulting. Thrust faults, on the other hand, exist at all scales, with some large thrust faults having displacements ranging from tens to hundreds of kilometers. Movement along a thrust fault can cause the hanging wall block to be thrust nearly horizontally over the foot wall block. Thrust faulting is most pronounced along convergent plate boundaries. Compressional forces associated with the colliding plates generally creates folds, as well as other thrust faults that thicken and shorten the crust to produce mountainous topography. Okay, so those were examples of dip-slip faults, so we either had normal or reverse, but now we have a different type. A fault in which the dominant displacement is horizontal and parallel to the direction of the fault is called a strike-slip fault. The earliest scientific records of strike-slip faulting were made following surface ruptures that produced large earthquakes. One of the most noteworthy of these was the Great San Francisco earthquake of 1906. During this strong earthquake, structures such as fences and roads that were built across the San Andreas Fault were displaced as much as 15 feet. Because movement along the San Andreas Fault causes crustal blocks on the opposite side of the fault to move to the right as you face the fault, it is called a right lateral strike-slip fault. Transform faults are strike-slip faults that accommodate motion between two tectonic plates. Although all transform faults are strike-slip faults, only those strike-slip faults that form from plate boundaries are called transform faults. Numerous transform faults cut the ocean lithosphere and link spreading ocean ridges. Others accommodate displacement between continental blocks that slip horizontally past one another. Some of the best known transform faults include California's San Andreas Fault, New Zealand's Alpine Fault, and the Middle East's Dead Sea Fault. Large transform faults like these accommodate relative displacements of up to several hundred kilometers. Rather than being a single fracture, most continental transform faults consist of a zone of roughly parallel fractures. While this zone may be up to several kilometers wide, the most recent activity or movement is often along a strand only a few meters wide, which may offset features such as stream channels. So you can see that here in the top graphic A. If you have a stream, perhaps flowing from the top right here down to the bottom left, well, if we move along the fault, the stream that was normally going across this area has to now be displaced, so it might move along the fault and then continue its motion. And last but not least is the concept of joints. Joints are among the most common geological structures and can be found in nearly all rock outcrops. As mentioned earlier, joints differ from faults in that no appreciable displacement has occurred along the fracture. Although some joints have random orientations, most occur in roughly parallel groups. Most joints are produced when rock and Earth's outermost crust are deformed by tensional stresses that stretch the rock apart and cause it to fail by brittle deformation. One way in which rock layers are stretched is in response to a relatively subtle region of upwarping and downwarping of Earth's crust. Regional upwarping of the Entrada Sandstone in the Arches National Park generated a set of nearly parallel joints. Joint patterns profoundly are affected by weathering and erosion of bedrock. In particular, joints allow iron-rich water to penetrate to depth and start the weathering process long before the rock is exposed. As a result, joints strongly influence how landforms develop. The iconic landscape in the figure formed as weathering and erosion enlarged joints, creating long, narrow walls called fins. These narrow rock walls, in turn, are the setting in which differential weathering created the park's famed arches. So in this case, you basically just have upwarping. We see stretching of the surface, so you get a joint starting to form. As a result, the dips in these rocks get bigger and bigger due to upwarping. Eventually, weathering will open these up, and over a long period of time, you get these kind of parallel structures like we're seeing up above. So let's go ahead and conclude this first half of the lecture with some quick questions. So number one, the movement of one part of a rocky body past another is known as what? Okay, so in this case, the answer is C. An everyday example of shear is the slippage that occurs between individual playing cards when the top of the deck is moved relative to the bottom. So shear is when one part is moving past another. Question 2. A syncline is a fold blank. Okay. Well, the answer is none of the above. A syncline is a downfold, or trough, with the youngest strata at the center. In an overturned fold, blank. Note this is question 3. So what of these is true for an overturned fault? All right, well, in this case, the answer is D. Overturned faults have it so that both limbs dip in the same direction, like we saw right here. Where is it? Right, am I losing it? Where'd it go? Okay, well, I think it was way toward the beginning. Anyway, so in this case, it's the youngest strata in the center. Excuse me for that brief moment as I was trying to find it. Okay, number 4. Normal faulting usually results from crustal blank. So in other words, what causes normal faulting to occur? Okay, in this case, normal faulting is when you are pulling the rock pieces apart, so you are stretching the pieces. And last but not least, in blank faults, the dominant displacement is parallel to the trend of the fault surface. Okay, so we learned about two main categories of faults, and in this case, it is a strike-slip fault. Strike-slip faults involve lateral motion. All right, as always, thanks for watching and have a great day.